To introduce Evan Zaffirio. He's at TGS Management Company in Irvine, California. He was one of Manfred Murari's early students, which makes him another grandchild of George's. Evan?
It's a pleasure to be here. As Richard mentioned, I am a grandchild of George's. Both he and I derive from the first son, which I'm not sure I see him here. But I have also a distinction, though I'm not sure if I'm the only person, but I may be the only person who also happens to have his diploma, undergraduate diploma thesis done with George, as well as being in his PhD academic tree. That was back when I was a student at NTU, National Technical University in Athens. And as you know, after the dinner yesterday, in the early 80s, Theos, God in Greek, was employed as a professor of chemical engineering at that university. And quite a few of us did a diploma thesis with him and ended up in the US. Yesterday, Thanos Panagiotopoulos said that he did not follow George's advice when it came to selecting in graduate school. And he came to MIT instead of Minnesota. In my case, I did follow George's advice to the letter. I went to Wisconsin to work for Manfred Murari. He prepared me for that. And he told me, go to Wisconsin, do not go to UT Austin, where I was going to work for Tom Edgar. That's going to be awkward because Tom Edgar is the first speaker. Okay, let's see, what can we do here? I will say, though, that George prepared me for Manfred. I did my diploma thesis that summer, and I thought I was ready to go get, I knew things about control, and then I go to Wisconsin and I find out, well, Manfred is like, yeah, well, it's all about IMC now. Forget all that other stuff. So I'm not sure, maybe I should have come to UT Austin. Let me introduce Tom Edgar. By the way, I really appreciate, George, that you assigned me to be chair for this session, because 10 years ago, when I literally abandoned process systems engineering and academia, I never thought I would get another shot at Tom Edgar. So this is really the last opportunity I have, so I want to make the most of it. Tom is currently the George T. and Gladys H. Sabel Chair in Engineering and Director of the Energy Institute at UT Austin. He has been at University of Texas for a very, very long time. Actually, trying to find the date here, but I think it's just about the days when Texas was an independent republic. I may be exaggerating a bit there, but it's a very long time ago, and I'm not going to give the actual date. But before going to UT Austin, he got his PhD at Princeton. It was just about the time that Albert Einstein passed away, but he didn't make it to work for Albert, but he worked for Leon Lapidus. And apparently, George knew of that work before he met Tom and thought very highly of that. And I believe they hit it off quite well after the first meeting. Now, I've been told that there are stories that Tom could tell, and George seems to trust Tom. I don't. So, be nice to George, okay? There's a long list of awards for, Tom has gotten just about every award that could be in chemical engineering and in control engineering as well. I'm not going to read through all of them. The most recent is the Richard Bellman Control Heritage Award a couple of years ago. One thing that is not on the list I have here that I know about Tom is that he's also a Hall of Famer. He has been inducted to the Hall of Fame for process automation about 10 years or so, and I'm not sure how many people here might be in that Hall of Fame. I think nobody else, right? A few? Okay. So I think it's safe to give you the floor now, and he's going to talk about manufacturing.
So as we learned last night at the dinner, you don't criticize God. So we're probably going to stay away from any sensitive topics. But I do have some things in here that reflect my past history with George. And I think we probably got to know each other in the mid-'70s, is my guess, for the first time. And we've sort of kept up with each other ever since. So I'm really pleased to be here and talk about manufacturing, which is an area that actually aligns quite well with PSE and it's something that I've spent a lot of time in the last 10 years, thinking about what we should be doing with manufacturing, broadly speaking. I should also, since people have been talking about family trees, so I'm not in the Stephanopoulos family tree. I'm in a parallel tree. So Leon Lapidus, of course, who was at Princeton, was a student of Neil Amundsen, which Minnesota connection, right? But more remarkable, the first two students that Neil Amundsen had were Leon Lapidus and Andy Akravos. So sometimes you get lucky in the beginning, right? And that helps you out your career, as you know. So, okay, so I think that I'm going to pick up George's timeline somewhere in the 1980s, and it actually happened that I was giving a short course on process control in Kuwait, and I contacted George. He was in Athens at that time, and said, "Hey, why don't I fly from Kuwait through Cairo, Egypt, and then come up to Athens, and then we can spend a day together or something." And of course, I ended up getting there with no baggage, and there was a whole lot. But he did buy me a nice T-shirt in Athens, so that was good. So, but we had a good time, and I think this first slide actually reflects a little bit about George's situation about that time. So this is George out on the beaches near Athens, okay? And so he says, you heard from the story from Manfred yesterday about he was very good at having women being interested in him. And so this was George's first attempt before he met Eleni of trying to get to know women in Athens. And of course, he had the higher mathematics working in his favor at that point. And we heard some discussion about the process control book that he worked on while he was in Athens and then come out. And of course, being now in a kind of a competitor position in terms of process control textbooks, although George did one edition, we're up to 4 now in our book, and with Seaborg, Mellenchamp, and Frank Doyle. So we've stayed with it longer. We actually started in 1981, believe it or not, with a short course in Santa Barbara, which I thought was a good place to have a short course. I think most you would agree with that. And so we actually developed some notes, and then George's book came out, and we said, okay, well, maybe we should wait a while. Let this one die out, and then we'll bring ours to market. So that was a little bit of the thinking back then, and that's, in a sense, how it played out. What I want to do is recognize George, and this was a discussion yesterday about his thinking about plant-wide control, that this was the first process control, mainstream process control book to talk about plant-wide control. And I just excerpted a couple of pieces here. You can see here a key paragraph in the preface that kind of hits the tone of what George was trying to accomplish. So again, very much deep thinking about how we think about plants and their control as opposed to individual unit operations. And this is just one of the chapters. Now, since that time, and even parallel to that time, a number of other people, and I've listed their names down here, who have been some of the pioneers in plant-wide control. But George was certainly among them in terms of getting people to start thinking about this idea. And I'm going to come back to that theme later in my talk today to talk about enterprise control. So here's a slide, and I actually remembered this slide because I got it from George. I don't know if you remember this slide or not, but it was actually at that time handwritten. This was not your edited version, okay? But you gave a talk around 2000, and you sort of said, okay, here's the way we need to think about the enterprise of process control. And so I still have a stash of 35 millimeter slides that I used at various talks along the way. And I remember giving a talk in around 2000, and I converted your handwritten slide to this slide. But this is the slide from 2000 that I had that I thought was a good start. But of course, today we've developed our thinking, and this in fact is instead of a 3-layer kind of model, this is now a 5-layer model, which most people tend to use to talk about process control optimization and supply chain. So, many people in this room work at different, parts of this, but maybe 2 of the blocks or maybe 1 of them. But the point is that that we still, like to think about what's happening. And there is, of course, a timescale issue when you look at this slide about things you try to do that are essentially, in the same realm of the time constants of the process. And then there are things you can do that are longer range and so on. But, this again is, and this this diagram didn't appear in our first or second edition, but in the third edition that came out 2004. So again, it's not been around that long, but it's been pretty much accepted now. But anyway, so this is where we end up with thinking about all the different levels of process control. And this is what George and I looked like around 1986. So you see there's some similarities, at least in terms of facial hair, if nothing else. And we're sort of, in terms of the hair on the head, we're very similar today too, right? So, so we all get older, right? So this is, of course, this diagram that everyone shows when we talk about neural nets. And I'm not really intending to spend much time on this, but again, just talk about George's involvement with intelligent systems or expert systems. And in fact, I was thinking that, what's the difference between intelligent manufacturing or intelligent systems and smart manufacturing? Is there a difference? Well, probably not. But in any event, the words keep changing, but they seem to mean the same thing. But certainly, this idea, the multi-layer artificial neural network, that caught fire in the late 70s and in the early 1980s, and people were trying to figure out, how do we use this in the process industries, and that led to expert systems. And so here's a slide, and Jim's in the audience today, so I can give him credit for this. He was talking about how MPC was sort of rediscovered multiple times along the way, and he found this quote from Goethe about everything's been thought of before, but the problem is thinking of it again. So we kind of have this going on with artificial intelligence and neural nets, machine learning, et cetera. It's happening today. And in fact, just about a month ago, or maybe a few weeks ago, Bill Gates was giving a graduation speech at Columbia, and he said, okay, AI, energy, and biotech are the three big deals coming. And whether we should believe him or not, but he's, I think, probably not too far off on that. So this is very interesting, but of course now we know that Bill was only 30 years behind George, because George was doing the Laboratory for Intelligent Systems back in 1986. So in any event, history does repeat itself, and George is probably getting out of being so active in this area that he's going to watch and see what happens here, I think, but I'm sure you'll be giving us advice on what we should be doing too. Now, back at that time, there was also a lot of interest in expert systems, and of course, most of the ideas were around, essentially the software required to do that. But there was also another school of thought then that, really it's not about the software; it's about really having experts. And so, and I'll show you a few of these jokes or cartoons from the CPC meetings that I've had a lot to do with. So this is the one that came out in 1986 or so, the Shinsky in a box, okay? So does anyone remember who did this cartoon? Because I know who did it. Anyone guess? No. Is Eric here? Yeah, Eric Itzdy. So that was one of his creations. So he was always drawing cartoons at the end of the meeting to kind of represent things. And of course, how we go forward with robots and artificial intelligence, might be summarized in this next slide. Okay, so that may be your plant manager of the future. And of course, this was also another funny thing that happened in one of the CPC meetings. We had a series of people, of course, people know about dynamic matrix control, or DMC. Later, we had someone give a speech, give a talk at the next CPC where they got confused. They called it dynamic maintenance control instead of matrix control. And then in CPC 5, we had someone from Shell who talked about he got the Pooper Scooper Award. So he said, even a dog can control Shell's Deer Park refinery. And so all you need, see, is the operator's there to feed the dog, and the dog is there to keep the operator away from the controls, okay? So that was the whole idea behind that. And then, of course, you remember this famous cartoon about, on the internet, nobody knows you're a dog, right? So that's from 1993, believe it or not, if you go back that far. Of course, now we know there's another phenomenon that occurs, which is that it could be somebody sitting on their bed that weighs 400 pounds. So that's not my first Trump joke. That's not my only Trump joke. Okay. So George has also received a number of awards, and actually some of them line up fairly well with some comments that were made last night as well as yesterday. So here's one that was called, in 1991, George received the Extended Horizon Award at CPC4. So here it is, for asking the longest question at CPC and sometimes providing long answers as well, but no acceptance speech was permitted. That one resonated, obviously. And then more recently in 2012, he gave a nice talk about how we teach process control. And so he got the Olympic Games Award for suggesting a new approach to chemical engineering education like the beer games taught in business schools, which he was quite familiar with here at the Sloan School. So in any event, those are two less well-known awards that George has received. So now let me talk and transition a little bit into manufacturing more directly. And some of this does certainly fit in because it's part of the things we try to do, such as data analytics. So, and I'm pleased that Jim Davis is here at the meeting today. And of course, Jim worked with George quite a bit on artificial intelligence and expert systems back in the 1980s. And then Jim and I got together probably 10 or 12 years ago when we started trying to say, okay, a grand challenge, actually that was identified by the National Science Foundation as one of 5 grand challenges about 10 or 12 years ago, which was manufacturing or smart manufacturing or intelligent manufacturing. And of course, the whole thing there is based on data. And this is one definition that we can use for smart manufacturing, which is the right data at the right time in the right form wherever needed. So, but again, notice the word enterprise is there. So again, smart manufacturing is, in a sense, from the very beginning, trying to adopt an enterprise point of view. Of course, you'll have some talks that you've had at this meeting on Internet of Things. So my example of why Internet of Things isn't the solution, or it's not the whole solution for sure, is the following. So if you want to figure out, okay, you decide you're going to go on a diet, so you're going to connect your smartphone to a digital scale. And then you'll lose weight, right? You have to do something else? Of course. So the point is that it's really the actions you have to take that are important, and it's not just the hooking everything together. So we've got to figure that out. And this is, again, kind of the standard thing we talk about, how many connected things are going to be out in the future. And again, other people will be talking about this in more detail, so I'm not really going to talk about it much here. But of course, now as we converge information technology and operations technology, then maybe this is the energy station of the future, okay? So we got ExxonMobil, of course, we know about them, combining with Microsoft and Amazon, okay? So, and this is maybe some sort of electric car coming in to not only get its power charged up, but also maybe a reboot of its information system or something like that, or its software. So the point is, this is something that's out there, and of course, it's interesting that as we track graduates in the area of process control, more and more of them are going to work for companies like Microsoft and Amazon, as well as startups and so on. So it's not too far-fetched that PSC is going to be a unifying feature of all this. So Jim Davis and I actually started an organization about 6 years ago called SMLC, which stands for Smart Manufacturing Leadership Coalition. And this is like a vision slide of all the things you'd like to try to accomplish. Again, nothing here is really brand new to most of you in the audience. But again, it's looking at not only the what's going on inside the factory, but also worrying about the supply chain and the customer side of it. You've got multiple objectives around doing things safely, sustainably, trying to do things in an energy efficient way, reducing emissions, and then of course a lot of that, the thing that makes it all work is having access to, first of all, excellent models, but also strong optimization capabilities. And I suppose all the work that Jim and I did in getting companies together, universities together, and trying to talk about, well, how do we develop a national agenda around smart manufacturing? There was actually a major project that got funded by DOE that I ended up being the principal investigator for. I'll talk a little bit about some of the specifics of that in a minute. But the point is that basically provided a launch pad to write a major proposal to the U.S. Department of Energy when they said they wanted to establish a Smart Manufacturing Innovation Institute. And so this is what happened, this thing called SESME. The CE there stands for Clean Energy, so it's Clean Energy Smart Manufacturing Innovation Institute. Was announced roughly a little over a year ago, and it was finalized or formalized in January. Of course, there's still some uncertainty now around what's happening as DOE gets reconfigured under the Trump administration. But the point is, the idea, it's a $70 million over 5 years investment by the government, and it's supposed to be matched at least 1-to-1. And this, again, is part of the series of manufacturing institutes that have been established across the country, supported by a variety of government agencies. And this was, in fact, the 9th one. There's also another one that's been formed. The 10th one is one that also has a lot of interest for chemical engineers. It's called RAPID, that AICHE is leading, that has just also launched this year on process intensification. So some of you are also, I know, aware of that one as well. So when you look at the stock DOE slide, when they were going around saying this is something they wanted to do, it's interesting that, I mean, first of all, I think Jim and I figured out that they read a lot of the literature we wrote, so they basically were able to transport that into a nice slide that talked about why you'd want to do all this. But the point is that if you read the different bullets here, you see process systems engineering embedded in everything here. And it's, it's around sensors, modeling, control, optimization. But this, again, is specifically addressing energy. But the good news is that DOE, I think, also takes the attitude that it's not only energy but also quality. You've got to worry about the trade-off between those things, because if you operate a plant just to save energy, you can have poor quality products, and that doesn't end up becoming a viable business. So let me talk about a couple of test beds that I worked on, and also Jim Davis and Michael Baldea, who's also a professor at University of Texas. So we looked at actually 2 industrial scale plants during the past 4 years as a way of demonstrating the value of smart manufacturing. And again, this is not intended to be say, oh, you guys haven't heard of this idea before. Certainly the ideas are well known to people in this room, but at the same time, applying it on a really large scale, which again gets industry interested. So we actually picked one process. Some of you know Larry Megan from Praxair. He arranged to basically run a large test on steam methane reformer in Port Arthur, Texas. And so this, you can see the diagram here, what it looks like. It's basically a facility, if you've never seen one, about the size of this building. So it's a good sized facility. What you're trying to do, of course, is take methane and convert it by reforming into hydrogen. So it's basically a hydrogen plant. In fact, this hydrogen plant is actually it's a captive plant inside a refinery in Port Arthur. And the idea is that you've got catalyst tubes. You're heating up, essentially, you're burning natural gas in order to provide heat to drive an endothermic reaction so you can make hydrogen. So you've got, in this case, you can see 336 tubes in this particular SMR, and then they have burners that are in the sense of the manipulated variables you have at your command, so you can vary the amount of natural gas going in order to essentially affect the heat transfer properties within the furnace. And the idea, of course, is that you'd like to have every tube operate the same and have the same, producing the same molecules coming out and achieve maximum efficiency that way. So this is, of course, again, one of the value propositions for why you would do that. This is a typical distribution before you apply advanced sensing and modeling and control. And you can see, again, it's a fairly widespread tube temperature. You do have to worry about the maximum temperature, because if you essentially have too many tubes that get to the maximum temperature, they're going to burn out, and then you have to shut down the unit, replace the tubes. So you'd like to keep be, as near to the constraint as you can be, but then also narrow that distribution. So that's, again, the goal of trying to balance the furnace. You can see we can narrow the distribution, and then we can shift it over. That gives us a higher conversion of methane, and then lower energy consumption in terms of making hydrogen. So we've been able to demonstrate that we can improve, reduce the amount of waste heat by about 25% in this unit, which was already fairly high efficiency, by the way, but you can still do some things in order to make it operate better. It's interesting that a complex system like this really comes with no control valves. They just basically run it, and they go around manually adjust things, but there's no automatic control. So we have really collected a lot of information about temperatures. In fact, you can see that we had cameras mounted on the side of the wall, so you could actually go in and look at the temperature distribution. In fact, you can see, if we're looking at an IR map here of temperatures, you can see that it's changing all the time, okay, based on the data precision that we have. And of course, you can go around and you can adjust the burners accordingly in order to essentially make the furnace operate more efficiently. But it's a big data problem. It's basically acquiring lots of information, and how do you reduce that? Okay, second example I wanted to briefly mention is metals processing, and this is one where you're essentially, use a lot of energy in order to heat up metals, forge them, press them, treat them, and then you end up machining them in order to make a particular kind of shape. And so we have found a second company that was willing to offer up a test bed, which was a company, General Dynamics in Scranton, Pennsylvania, that operates an Army ammunition plant. So they're making pretty good sized shells. You can see some of the pictures here. Basically, the particular system I want to talk about in a little bit more detail is a heat treatment furnace where they carry out austenitization. And you're basically putting these metal billets on a conveyor belt as it gets heated up. And so it becomes, if you're trying to model this, you got all the modes of heat transfer you're worried about, as well as essentially moving boundaries, and it's a set of PDEs that you have to solve. And so it really offers the opportunity to do model-based control and model-based optimization. So here you see again what's the final products look like. Those are about 18 inches tall, and you can see again what happens inside the furnace. It's under a nitrogen blanket. The big challenge is, okay, how do I, first of all, operate this furnace at maximum efficiency and save energy? But then you also have to pay attention to the quality issue of, okay, what's the nature of the metal properties after I do the heat treatment, and what's the crystal structure look like, and so on. And because if the crystal structure is basically forms large grains, then you're going to have a lot of defects when you essentially get to the end of the line and do the machining. And in fact, if you look at the cost of energy versus the cost of defects, the cost of defects is definitely a lot larger in this case. So you basically need to be able to model the materials properties, which unfortunately are not super well known. And you can model, again, what happens as a function of time with a part going through as it gets heated up, what the temperature distribution looks like as it moves through the furnace. And again, I'm not going to talk about the graph in much detail. You can formulate a nonlinear programming problem in order to say, okay, I want to have the right things happening, minimize energy usage, subject to certain constraints on temperature. But then if you look down here about the temperature uniformity, that would be the temperature spread constraint. And then finally, if you have this embedded in a materials model, you can then essentially put some restrictions on grain growth so that you actually make sure that not only can you save energy, but also make the products that are essentially you're not going to be throwing away, but are in good shape. Well, I think I say something about PSC and manufacturing and jobs. Okay, so here's a number of the politicians, thinking about, okay, how does the U.S. bring back manufacturing jobs? But of course, we know who has the answer. Okay, there he is. So, a lot of talk around manufacturing and how we bring jobs back. There's really an excellent article I would suggest people Google and find by Atkinson and Ezell that talks about all the aspects of this, that it's really a complex question and certainly been oversimplified by the administration. But the point is, those jobs have gone away. They're not coming back. And if we brought them back, we don't want people in this country making Happy Meal toys and other things that low cost production. And so really, this is where I think PSE comes into play. That we can become, and if we're worried about the U.S., and I realize there are people from other countries here as well, but if the U.S. wants to be a leader in terms of manufacturing and basically increase the job base, then we have to be identifying those jobs that are essentially high value added, and figure out, well, some things may be performed in other countries better than we can do it or cheaper, but we should identify those industries that are maturing that require a high level of intelligence in order to make the products. And one example they cite in there, is, interestingly enough, is that Germany has a trade surplus with China. So it's not that it can't be done. Well, let me talk now about manufacturing and the three components of smart manufacturing. So the three things, if we were to identify them in the context of PSE, it's basically this factory enterprise integration, exploiting the intelligence of manufacturing, and then having disruptive business models. So we can, as I showed you in that diagram of the vision of smart manufacturing, we want to essentially optimize for profitability, but have minimal environmental impact and abnormal events. We want the process to become more agile. And then finally, we need to have computational methods that are going to be able to handle the supply chain and figure out how to do flexible manufacturing and dealing with uncertainty. So models are really the key element of this. I think that we understand that when we're trying to do control, model helps us figure out what's going to happen down the road in terms of the performance of the system. And we can the thing that's really changing in manufacturing, though, is that we used to make molecules like methanol, ethylene, and things like that. Now we're going to be focusing more on polymer blends, solvent mixtures, metal composites like I talked about, electrolytes, and so on. So that's going to put a lot more of a burden on the modeling people, and trying to characterize the whole supply chain from a molecular level is important. So let me just wrap up here. We've got to have improved accuracy of models, especially for some of these new kinds of products. I think we're going to see a lot more high-performance computing, but still mathematics is going to be a key element of PSE. But the other problem, of course, is that who's going to be able to take care of the models? Where are those people going to come from? Because it's not something you just kind of hand over and not have people who can know how to take care of them. So in conclusion, basically, I think that smart manufacturing paradigm, I don't have to argue with you too much about what that is, but also that certainly that aligns with PSE, and that bringing in PSE and ICT, or information and communications technology, is going to help us be more broadly applicable to not only large enterprises that we know about, but also small, medium ones. And I think George certainly is really one of the early thought leaders in this area of plant-wide control, plant operations. So at the end here, after a long distinguished career, what's left for George? This dog kind of represents maybe the way I feel some days as well, George. So I thought of one thing. I think you said something about traveling more, and so I thought that maybe we should include this last slide here about maybe what some of your travel plans might look like. So thank you very much.
So there was a conference in Germany last year that I happened to be, and they had invited 3 politicians. And I was impressed by how much the politicians were informed about technology. And one particular thing was that the guy said, you all academics, in 5 years, you're not going to be able to do any research without having a data technician or a data curator in your group. Where are these people coming from? What degrees do they have? They're obviously not going to be Herr Professor doctors, but somebody has to make a career plan. How do we educate them? Where do we go? I was amazed because I realized it's true. I was very much amazed because it seems that their politicians seem to think about technology and what we need, while here there's not very much discussion about it. You said who is going to take care of the models, who is going to take care of the data. What are these people going to be, and is NSF ever going to fund them? No. Anyway, thank you.
Yes, there's actually, at the last CPC FOCAPO meeting, there was a session where they talked about data science, and the company said, you know, if we can find a chemical engineer who's also a data scientist, that's the best solution for them if they're in a chemical company, but now it's, you know, there are still lots of people just hiring, you know, computer scientists who are data scientists, or people who, you know, there are online degrees on data science now you can get a master's degree, so there's lots of options for people to pursue, but I agree that, you know, the administration is kind of tone deaf about some things. That's one of them probably, so. Yes?
I'd like to add, basically, one of the issues in applying many of the technologies that are being talked about yesterday and today is that, you know, a chemical plant is run by people with bachelor's degrees in chemical engineering and operators who are high school grads and maybe a little college. And all of these techniques, if they're going to be applied in manufacturing, have to be improved in the sense of the front end such that they're easy to apply to a variety of things. And so while, you know, the underlying technique is great, if, you know, who's going to create this into a software package which is going to appeal enough that they're going to want to use it, and, you know, that same guy with the bachelor's degree also has to buy it. And so, you know, it has to look relatively easy to him so that he can do it in his limited time. And nobody so far has talked about making these techniques user-friendly. And that's a real issue. It's an issue for the robotics people too, for manufacturing in the 21st century. If it takes a team of 10 people to put a robot in place and they all have to have engineering degrees, many of them graduate degrees, you're not going to have that many robots. And the same is true with many of the techniques that we discuss here.
Yeah, that's true, and I think that the software is becoming more complex, unfortunately, instead of less complex, so that's going to be a challenge for the vendor community for sure. So maybe the AspenTech people will talk about that in a couple of talks later. So, all right.
Thank you again, Tom, and especially thank you for being so nice to George. Our next speaker, as I mentioned earlier, we are academic. Let me, a second here. So our next speaker, as I mentioned, we're academic brothers. So we derived from the first son, who actually is here now. And he finished a PhD at Caltech and went to University of Illinois for a few years before coming to MIT. He and George have been colleagues for some time now, and they work closely on educational and developmental matters. Now, Richard has a very, very long list of awards here. I count 13 awards, but you can find them all on the MIT website. So since this is a kind of an extended family get-together, I thought I'll mention an accomplishment that goes back to his graduate student days, because all these awards are from his faculty days. So when he was a graduate student, he was younger than I, and at some point, he came up with the proof that the computation of the structured singular value, for those who remember that, is actually NP-hard. That may sound esoteric to most of you, but in those days, a lot of us thought, well, the kid is really, really smart. So that was quite an accomplishment, and it was actually a eureka moment for Richard in more ways than you may think. I was not at Caltech, as I said, but an eyewitness from those days has relayed to me the announcement, the way it was announced for the first time to the world. So one morning, apparently, Richard walks into the office, but not his office. There was nobody there. He walked to another office with other students of the first son. And the way it went was this morning I was thinking in the shower, and I realized the computation of the structure singular values NP hard. So it was a eureka moment. It involved the bathtub, and also he rushed out to announce it to the world. I believe he did put his trousers on before he did that, but that's the second part of the eureka moment. And like I said, long list of awards, read the website, it's worth doing that.
Thank you for that introduction. Definitely my best ideas I had as a grad student were all actually in the shower. So, so I'm going to talk about advanced manufacturing, and I think the timing of this talk's great because I've had a nice warm-up with Tom Edgar talking about smart manufacturing. And some of the stuff I'm going to talk about is going to be related to some of the topics from the previous day. But hopefully I'll give you a somewhat of a different perspective. First, I'm going to start off with some definitions. Then I'll talk about a vision about advanced manufacturing. I don't have time to talk about data analytics and all the other stuff that the group does. So I'm going to really focus on really one specific vision. And then I'll talk about a sketch of some things that I think needs to be done to realize that vision. And then I'll talk about just one platform that we've been doing. We've actually done a whole series of platforms along this sort of idea of advanced manufacturing, and then I'll close. So what is it? So here's some definitions. Of course, the first place you go for anything is Wikipedia nowadays. So the use of innovative technology to improve products and processes, high rate of technology adoption and ability to use that technology to remain competitive and add value. And then the White House report in 2014, manufacturing that entails rapid transfer of science and technology into manufactured products and processes. So I think these definitions are fine. When I use the definition in my own group, though, I focus more on something that was referred to at the end of Tom's talk, which is really products in which there's a very high value added in the process. So typically in my group, we'd focus a lot on, let's say, pharmaceuticals and biopharmaceuticals, where you've got like carbon, hydrogen, oxygen, maybe a few nitrogen and phosphorus, and then tens of millions or hundreds of millions of dollars come out the other end. So tend to focus on those sort of industries, and also where the products are very highly structured. They may have molecular structure. Molecular structure, of course, will be important, but also like crystal structures and microstructure and so forth, which was something that was also alluded to in a different application in the previous talk. Now, the previous talk was about smart manufacturing, so I knew that was probably going to be the topic before, so I'm not going to talk too much about this. But these were terms that were raised in yesterday, and so those are all things about smart. I like this one, which I heard at SMLC. Somebody said smart manufacturing is smarter than what industry is currently doing, or what your industry is currently doing. So that's the other ones you've all heard before. So instead, I'm going to focus on a particular vision, at least how I see advanced manufacturing. And part of this is also to address the question that was the last question to Tom about how do you deal with workforce and how do you deal with the user skills in terms of operators. And so this is a project, this is the second DARPA grant that we had, but this particular thing here I actually pulled off the DARPA website, so it's all publicly available. And so DARPA's been funding quite a bit of research in chemical engineering and manufacturing. And this one, particular one, the title happens to come from something that Klaus Jensen came up with here at MIT, which is an automated systems for knowledge-based continuous organic synthesis. But the text that I have here are all basically edited versions that I sort of condensed from a DARPA website that defines the general program that funds our particular system. But what we're building is a fully automated chemical synthesizer that produces, purifies, characterizes, and scales a wide range of organic molecules. And the thing about this is that what we're trying to build is we're trying to build something very similar to when you request things. So the idea is you would have a box, let's say the size of maybe a refrigerator or so, and you would walk up to the box and you would say the name of some compound. And so maybe you say aliskiren hemifumarate, as an example. That happens to be a drug compound. And then you say, well, you could say a bunch of things. Make it so, hook me up. I don't know. So some kind of catchphrase, so it knows that it's not taking the word out of casual conversation. And then Suri, hook me up, and then bam, it makes it. Right. That's really what the project is. And DARPA has a lot of these sort of considered DARPA hard problems, but it makes you think about how can you really make everything really not just automated, which of course our community's been doing for a long time, but really make it more autonomous. So the idea is you're not just automating valves and sensors and equipment, but you're also automating as much as you can, the design process, right? So you're automating the control engineering, the separations, all of that, MPC design. So all of this being really an autonomous exercise where you specify a goal and then you have the system, in this case, making a chemical plant in the system using robotics, et cetera, and components to then make that product without the user having to have a high level of expertise. And so the inclusion, so what would this include? How would you try to do, this kind of a crazy kind of idea? So one of it turns out the main technical stuff that we're doing the most advances as a team has to deal with knowledge-based computational tools, and really about not just reaction pathway prediction, which has been a studied problem, but process flow diagram prediction. So how do you come up with candidate process flow diagrams and figure out how to rank order those and get that information from combinations of machine learning and computational chemistry. Then there's the process automation and control. Of course, this is something that we all do. This is, or many of us in the audience do. What's different about this, though, is that we were trying to do it so it's fully autonomous, so there's no tuning. There's no person control engineer tuning. Do this so that it's completely a process done entirely by the computer. And then there's the equipment. So these are all fluidic modules. These are sort of microfluidic, millifluidic kind of things that have all the inline characterization, purification, formulation as the equipment, which basically is like a library which you pull from to compose your processes. And then why would you want to do this? Now, some of this was discussed in the previous day, where someone was mentioning certain advantages in terms of having small-scale systems. So I won't talk about that too much here, but one thing that would do is allow you to speed the pace of chemical innovation and provide accessible chemical synthesis. And so accessible is a key word here to non-specialists. Now, here's an example that shows that a lot of the hardware we already have. So this is a previous project that Klaus also had that was funded by DARPA, which was this kind of refrigerator-sized system. It didn't have the autonomous part, but it was a fully automated system that completely ran, and it does all of the different chemical synthesis there. And it could do multiple syntheses within the same system. So how does this relate to George? So now I'm going to George. So I decided not to put George at the beginning, I put George on slide 3. So, because this is integrated pretty well to what this is. So many of us hopefully are familiar with Modela, but for people who aren't, that's the symbol for Modela. This was one of the projects that came out of George's lab that was also mentioned briefly yesterday. But it's a computer-aided phenomenon-based modeling laboratory that supports synthesis, modeling, and analysis activities in chemical engineering. And you can see the Modela is from Model LA. Modela enables process models to be constructed in terms of interacting physical and chemical phenomena written in English-like syntax, not as sequences of hardwired unit operations or sets of mathematical equations, and based on assumed phenomenon structure, the complete set of equations is derived. And this, clearly this was focused in part related to the question in the previous part about trying to make tools more accessible, but also to make it more efficient, make it a more efficient exercise. So what I want to do is I want to compare this to what I just talked about. So this is actually the same, right? So we're building systems in which we have synthesis, modeling, and analysis that's just integrated into the system. And that includes uncertainty analysis and optimal control, et cetera. And then the second part we're clearly doing too, because we're also deriving first principles models for everything. Now that's enabled because we're doing small modular units, so the flow patterns are simpler. So I agree with that, but that's okay, right? We're if you don't like a control problem, you just define a new control problem by changing the process, right? So definitely as a team, that's also what we're doing. And we're constructing all of the equations fully automated. So in the system, the plant, as is put together with the data structures, it just constructs dynamic simulations in an automated fashion. I'll talk more about that in a few slides. But the thing I'd say that's really quite a bit different is really replacing step 2 from Modelo, which is this part is about constructing for interacting with English-like syntax. So what we're doing is we're replacing all of this to make it fully automated. So that's really what the difference is to replace the step with automatic constructions of process flow diagrams. So that's a big part of our agenda. So what I want to do and talk about now is what needs to be done to really make that into a reality and to try to make that into a reality. So this is what we're doing. So first is increase understanding and optimization of each unit operation, exploiting process intensification. So we're building and designing very intense processes in the team. High surface area to volume ratios, easy to control, high gains, fast dynamics, small time delays. So things that make the control problem a lot easier. Process intensification is for all the different reasons that you've probably briefly alluded to yesterday, but it includes cost savings and efficiencies, and also it turns out it makes control problems easy as well. So it makes automation of control a lot easier for this kind of system than what it would be like for a refinery, for example, where you don't have things so intense and you have large time delays, slow time constants, and low gains often. Automated high throughput micro scale to maybe millimeter scale kind of technology for fast continuous process R&D. Now Shinji talked about yesterday about, Hasebe talked about the advantage of continuous, and continuous is actually good at the small scale too in terms of surface area to volume ratios and controllability and operations. So I won't talk about that here. This happens to be a picture of one of our collaborators in terms of one of the bioreactors that's done in micro scale. This is a system that's about the size of a double-sized card deck, but it's very high densities. Plug and play modules, so we're designing everything to be plug and play, so you just connect them together. Integrated control and monitoring equipment to facilitate the deployment, so the people can use the modules without any background in control or operation. And again, this is made a lot easier because of doing things at the micro scale. For example, for reactor control, it becomes very easy when you have very high surface area volume ratio. You don't need to even have models coming from upstream calculations. You don't even need models to even know whether it's exothermic or endothermic. You can just take your whole reactor and put it in an oven. You just control the oven at constant temperature. And that's easy to do at surface area to volume ratios are very high. And then it's all sort of plug and play, so you just connect the different together, standard connectors, so straightforward. For the user. All the models are dynamic, and we need that because we're building models to do all the startup, shutdown, and transitions also completely automated. And so that's really important. It's also important to model the disturbances and the uncertainties because that's the part that actually leads to reductions in control performance. That happens to be a previous plant that we built with a bunch of collaborators here at MIT. And then really autonomous. So how do you do autonomous model-based control technologies? And so this is sort of the components, I'd say, of what needs to be done to sort of realize a sort of 2040 kind of vision of control. Now I'm going to say some things now here that are going to be probably well known to control engineers, but some of the audience aren't. So I'll just say it very briefly. So what we're doing is everything we're doing that we're building a virtual plant, so a plant simulation, dynamic simulation. And that simulation is very, very heavily first principle. So essentially all first principles except for calibration of sensors. And we're doing that because what we're going to do is our MPC problems, our control problems are very different than what you have in the oil industry. So let's take a little sideway about the oil industry. So typically you design an MPC controller. You already have all the regulatory controls in place, and then everything's running, and you're collecting lots of data. Lots of data is collected. Then you do experiment, collect lots of data. Then you build models, typically step response models. Actually, first you do state space, usually converted step response, but that's a detail. And then you tune your controller. Okay. But what we're doing in this case is very different in that in this case, we're having the control start from zero. So this is a fully automated system. So instead of setting it up with a bunch of operators, we push a button and the full thing's automated. Now, we've already done this multiple times in the group. So we've done it for one small molecule process that I showed the diagram of before. That was actually done back in 2012 with a variety of individuals, including Klaus Paulbart and many others. We've been doing it for a biosystem, which I'll talk about soon, which that one actually was done, I think, 2 years ago. And we're working on other systems as well. So these are fully automated systems that we don't have the data. And so to get that information, we need to be high up in this sort of pyramid where we're really getting first principles, because we don't have data yet that we can use in our control design. Now, we do a lot of high complexity modeling in the group. So we do, CFD and CFD with particles and things like that. But we only do that in the design stage. This happens to show an example where we've done a bioreactor. We do that in the design stage to design the process to be really easy to control, really easy to operate, and really high quality. So that's really our goal here. But that's not the models we actually use when we feed into the control systems. What we do is we have lower complexity models. And so after all this stuff has been designed very well, we can use very simple type models, well-mixed tanks, a couple of the tanks in series kind of models, for example. Here's an example of one we use for one of our static mixers we use for process intensification. It's a standard tank in series kind of model. And those are the stuff that we need for control and operations. And so that's actually the stuff we use when we compose our dynamic simulations for process control and monitoring. And the goal for all of this is right first time. So the idea is when you start up the process, it's right first time, and everything's on spec. Now, what's difficult about this is that there's a very different situation in pharmaceuticals than it is, or for many high-value products, than what you would have, let's say, in the large chemical industry. So if you have a refinery, let's say you have some gasoline, and let's say you have a little bit where the octane is just a little bit, below what it should be. Do you care? So you're going to lose a little bit of energy maybe, but you're going to put in a gigantic tank. And if you have a lot of the other stuff is a little bit above octane, the overall average octane is okay, everything's fine. That's very different when you're looking at a lot of high-value type products. High-value products very often have to be everything on spec. So let me give you an example. So if you have like bad tablets and good tablets and you mix them up, can you sell that? Well, you can't, right? So actually, if you have one tablet bad anywhere, that entire lot has to go. That could be $10 to $20 million goes, right? So just for having one off-spec product. So you can't, in some sense, mix away your mistakes. So you really have to have everything right. And when we design these systems for these automated plants, we're designing them so that we have, our focus is not like speed to steady state or anything like that. It's actually making the product quality on spec right away so that there's no wasted product. So what else is available and what's needed really from a control perspective? Now, it turns out one of the things that helps us is plant simulation software, and there was a talk about this just yesterday, talking about GPROMs, basically. But the best commercial plant simulation software is actually pretty powerful. I mean, if you compare the power with the best-in-class methods with what's available in most of industry, it's actually pretty powerful what Chemy's been able to put together. But you can already handle nonlinearities, time delays, unstable zero dynamics. It just means, that's just a technical term meaning non-minimum phase behavior. Constraints, mixed continuous discrete operations, and some uncertainty analysis methods such as sensitivity analysis and Monte Carlo simulations are just built in. And so that's stuff that's certainly been available. It's actually been available for a while. There's a variety of vendors you can go to that have software that has certain pros and cons, but are all dynamic simulation that have these kind of capabilities. We tend to use more advanced uncertainty analysis tools usually that can either be integrated into the software, which makes it really fast, or you can have wraparound software. And so these involve techniques such as polynomial chaos expansions and such. And these things can allow you to have much, much faster performance, especially if we're using those for feedback control. Now, one thing that's very different about the uncertainty that we use is that we use probability distribution functions. And this was talked about by Professor Panelides yesterday. Most of the literature is focused on worst case uncertainty, which is very unrealistic and not very informative. It's much more useful, and what comes out of system identification algorithms are uncertainty descriptions such as this. So this one is constructed actually from Markov chain Monte Carlo MCMC. We did this, I think, like a decade ago or so. This happens to be for a crystallizer based on real data we collected in the lab. So this is just showing you what the uncertainty is. And so the thing is that all the methods that that's been working on is this kind of information. That's a lot more informative, a lot more useful to feed that kind of information, and much less conservative to feed that into control algorithms. So we're spending a lot of time really doing that for the last 15 years. A lot of the problems we look at for high value added for advanced manufacturing involve distributed states. So I mentioned how often you can make things simpler, such as getting simple flow patterns, but often you have other things like particle size distributions and other things that give you distributional states. So they're distributed in terms of some other variable or some kind of smooth function rather than being discrete. But there's techniques like moment analysis, various transform methods, method of characteristics, finite volume methods that we typically use to handle that. These are not well integrated into the various software packages that are available. So this ends up being stuff that you end up mostly just deriving yourself, which is great because I love math, so it's a lot of fun. But this is something that you can't necessarily just give to someone without too much training. But that's okay. The person who's doing this kind of stuff and building the components for the system, the software is then moves with that component. So they stay together and they move together. So when you can put all the plan together in an automated way, you can use the components without understanding that this is what's actually in the simulation model for each of those modules. That's basically transparent. The user doesn't see that. So it just needs one person to know this to build in the modules to make that work. And this just shows an example from our own lab of, example of distributed. This is roughly a two-dimensional distributed in terms of like a two-dimensional size distribution in that case. More research is really needed in automating the tuning process. So trying to make it so that it's not lots and lots of tuning. And so we've done a lot of work in that for the last several years. I think more work needs to be done. One of the things that we've been doing is we've been building it based on realistic uncertainty description you get from system ID that can be constructed automatically. So you can design your MPC controllers where you can just focus on performance. So if you look at the way you implement an MPC controller in practice, what you do is you get a step response matrix, and then you might get several of those, and then you sort of choose those, and then you go ahead and do a lot of iteration and a lot of tuning to try to tune things. But there's no uncertainty quantification, doesn't show up. So what you end up doing is a lot of the stuff you're tuning is you're just sort of tuning things to deal with stuff that isn't quantified. And so you're sort of trading off between different uncertainties and performance. And so you end up getting a lot of tuning parameters doing it that way. And so in this way, what you do is you would have the uncertainty come in, and then you just optimize the performance, which is specified by $ or whatever it is that has value. And then you can get rid of a lot of that tuning. At least that's what the supposition is. We've worked a lot on reducing online computations. I think more work is still needed. But there are now MPC algorithms that do robust MPC that are almost as fast as, they're within the same kind of scale, the same kind of order of magnitude as nominal MPC algorithms. Proofs of stability are very well established for MPC. So we're starting to get proofs of stability for these kind of uncertainty descriptions that you would get from system ID. And then optimizing startup, changeover, and shutdown, again, right first time. So everything's always right and not producing wasted product. And as you probably know, the easiest way to save energy, right, is don't produce defects, right? So if you can drive defects to zero, that's just immediately win in terms of clean energy, for example. And what I mentioned before is that the thing that I think, or I'm hoping, at least what we're doing, we hope and we see more people are doing, is to really do this time-invariant probabilistic uncertainty, or slowly time-invariant probabilistic uncertainties, things like that, because that's a lot more realistic and a lot more information-rich than just trying to do uncertainty in the sort of traditional way. So now I mentioned we've already been doing platforms. We've been actually doing this now for more than 5 years. I'm not going to show the first platforms that we're doing. I'm going to show somewhere in the middle. So it's not our current state-of-the-art, and it's not our oldest. And this one is for a biopharmaceutical on-demand platform. It's similar to what I showed before. It's a refrigerator, roughly, and you go to it, and it makes stuff. Okay. In this case, it makes drugs, and it's all made biologically. But the same system makes multiple drugs in the same system, just like the previous system makes multiple organic chemicals in the same system. So it's a multi-product system. And so what this has really been driven by, this is another DARPA project in which what we're doing is there's a lot of talk about personalized medicine, but personalized medicine can't really follow the normal timeline. So personalized medicine is where you take some cells from a patient and then from that, you can do some requirements and then design the drug, make some modifications. So this has been a lot of literature on this, especially in the biology field. But to do that, you can't really do the way drugs are made today. So drugs are mostly made with biopharmaceuticals. It's typically about 5 months or so from starting to end, and that's just too late. So, and so what people have to do is come up with things that are a lot faster. And some things are already implemented, like cell therapies and so forth. But you like to speed a lot of this up. You'd also like to speed it up so if you get something like a SARS or some major outbreak, that you can very rapidly produce medicines for that occasion. And that's another reason to be able to produce things rather quickly, or in some sense on demand. And so in this case, the idea is to have flexible methodologies for very rapidly modifying the cells to synthesize multiple products, develop flexible, portable, modular device platforms for manufacturing multiple biologics with all the nice properties we'd like. And then again, this is end-to-end. So this actually was this was our second end-to-end process that we did, again, on a small scale type platform. So to give you a little bit of background, is what we have here is an example of sort of a high-level view. We've got a bunch of parallel bioreactors, and then that feeds into a bunch of parallel columns. I'm only showing one of them, but we actually have a whole bunch in parallel. Feeds into some more polishing type separations, and then sort of feed. And so that ends up being, a schematic of what's going on. It's probably easy just to show some pictures. So the cell type we're using happens to be yeast. So this is genetically engineered with a collaborator that we have who's, of course, doing all the genetic engineering parts, Chris Love. And this is basically, we're using something that's very similar to yeast. It's called Pichia pastori. It can be lyophilized, be put in packets, so very, very similar. This shows the bioreactors that we used for generation 1. So that was another collaborator, Rajiv Ram, in electrical engineering. The bioreactor is actually on the top here, and then this is some electronics that fit down, fully controlled design system. And this basically has all of the different fluids that are fed into the system. Here shows another picture. So this has been popped up. This is the top part. And then this here is the bioreactor. And these are all little channels or little bioreactors. It basically gets so dense it's like toothpaste, basically. So it's a very highly condensed system. And this shows a bunch of them stacked up where you can see the different media and other inputs. The other things are separations. Separations look more like standard technology, but there have been some improvements there as well. So what are we doing there? So it's a multi-product plant, continuous and discrete. It's got all the different characteristics I mentioned, but we need to have no off-spec product. The approach we're taking all goes back to George again. So what we're doing is that we needed to automate also all the things involving plant-wide control. There was discussions about plant-wide control yesterday, as though that was a black box, but we don't find it really that much of a black box. So there's very systematic techniques you can codify that are described, for example, in the Stephanopoulos and Ng paper. So we just codify those methods involving sensitivity analysis and stuff that constructed automatically by dynamic plant simulators. So it's actually, that's actually not that hard to do the automation for these kind of systems because they're designed to be high gain, fast dynamics. So that it makes all the controls a lot easier. So it makes it'd be harder to automate if you have a bunch of recycles and a lot of complicated stuff, flow patterns, but that's not what we have here. And then we employ algorithms that handle all these different properties. So this is basically things we do. I think I have 2 slides left. So we have. So we, again, build first principles. We have local control, so each module can just move around as a whole system. Evaluate performance in simulation, propose design modifications, implement and verify separately. And then once we have that as a module, we can compose that into simulations. We compose that physically as well as in software. And so that's how to do it. So these are the 2 biological drugs. That was version 1.0 system I just showed. We actually are already in 4.0 now. It just got delivered. We're now doing the testing for it. And it just keeps getting more and more advanced. These were just happen to be 2. This happens to be a high dose type compound. And we met all the purity specifications for something that you could deliver to someone. And so it's end to end. So you seed the bioreactor. And actually really fast, it shows here, in 2 days, in less than 2 hours, you can immediately dose someone. So usually it's about, it can be, not always 5 months, but usually, maybe 1 or 2 months to 5 months to do the start of seeding a bioreactor to product. In this case, the entire process is around 2 days. And that's really mostly just growing up the bioreactor. So, and that's how fast. You can see that some of this is like, this separation is only 0.17 hours, et cetera. So very quick. So you make things very small, very quick, very agile. So you can basically make biopharmaceuticals on demand. Again, it's fully automated. You just push a button, fully runs. You walk away, it runs to just producing output. It's continuous. So when it starts producing, it just keeps producing output, just keeps producing. So we run it for about 10 days or so with no errors. So to close. So George. So I've known George for a long time, and I've appreciated, especially our more close contact. We co-teach classes together. We talk a lot about control education and research. And thank you for all your contributions. Thanks.
Thank you, Richard. Any questions? Go ahead.
Sure. Thank you. Enjoyed the talk. Tom made the comment about how the cost of defects was greater than the cost of energy. And I think as we get to making higher value-added products, that's going to be true. The cost of making garbage is going to be very expensive. And as I was thinking of that, it reminded me last week I was in Baltimore. I spent 5 hours at Baltimore-Washington International Airport, unintentionally, watching a very beautiful thunderstorm come through. And so my question is, when you design plants, or automated plants, when you optimize the plants, are you considering, or how do you consider, I know you mentioned uncertainty, but what happens when something breaks? What happens when your membrane has an issue?
Yeah.
What happens when
Yeah.
there's like a major
Yeah.
concern?
So
How do we design for that?
No, that's a great question. So we have designed that in. So that's a great question. So the way you set it up, right, is that you have basically a library that you can switch in and switch out any unit that breaks in the system. So it's just swapped out. These are very small systems. And so with modern robots, even not advanced one, moves things around and connects back. These are all common connectors and stuff. So it ends up being just replace. Now, for some of the specific equipment, both in my lab and as well as in Klaus's lab, what we also do is that even if something comes out, we have it designed so when the equipment comes out, let's say it's pushed outside of the box, we've got our equipment designed so that, like in our tubular reactors, for example, and our tubular crystallizers, we have it threaded in such a way, the way we design the heat exchanger system and so forth, that we can just take the tube and replace it with another tube, basically snake it out and snake another one in. You have to think about how to do that. It's a little bit of monkey business for like 6 months to figure it out. And then that tube is actually, in our group, it's usually like $100. So, and we just throw that away and we just have a new tube. And we get to keep the rest of the system too. So we're able to keep it very cheap. So that's how we've been able to do it, just swap in and swap out. Now, there's another thing which I didn't talk about. We also do is mathematically. Let's say something breaks, and it breaks, but now you've got, let's say, bad product. Okay, so the other thing I didn't talk about is we also built in little diverters. So we convert through the residence time distribution through the whole system at any particular location. So when anything breaks, you swap that out, and while you have the off part, you have a diverter there carefully placed with the residence time distribution. You know exactly when you need to do a diversion. That's running while you do the swap, so swap, right? The other guy, then that goes off to the guy maintenance, replaces the tubes, right? So then you can put that as a new backup into the library. And then the new system's in, you know from the residence time distribution when to click in, you just click it back in. So yeah, we've given talks about that. We've thought about all too. Because in this case, defects, like you said, defects are actually critical, right? At least for the health applications of the kind of technology that I've talked about. It also saves energy, like I mentioned, but it's actually the defect stuff is the more valuable. So, good question.
We need to keep this very quick. One last question.
Thank you for the interesting talk. And about the value of the pharmacy, the most significant value is not from the material but from patent, right? So my question is, do you think is it possible to include the phase of discovery of new drug into your integrated system, or it's a completely different story?
Yeah, so that's a good question. So we have not been focusing on developing inventing new drugs with this equipment. But clearly this would facilitate that, right? Because you could dream up a compound and then just have the system just make the compound. And then you could run that to your preliminary test and then start feeding the series of tests you need to see whether that drug is safe, efficacious, et cetera, through the system. So it would definitely accelerate that process because you can make things very quickly that a chemist can dream up. And so that it definitely fits in there. But this technology doesn't need to be really modified for that purpose. So they could just use this technology the same way. They would just use it in the drug invention lab. So that's why we haven't focused on it, because it's the same technology. So it doesn't change what it's not trying to do is it's not trying to do what's inside the guy who's trying to dream up drug molecules. So it's not replacing that part. It's somehow, I don't know how to automate that part. That's too hard. So.
Thank you, Richard. Our next paper comes from AspenTech. Before I introduce the two speakers, I have a question myself. I'm kind of curious about something that they may be able to help answer. I work at the quantitative hedge fund, and it's a space that is quite separate than process systems engineering. When it comes to the number of employees, we're rather on the small side, and yet there have been 4 people from George's academic tree that have worked there, 3 currently, 1 retired. And that got me thinking, what about a company like AspenTech? And given George's long association and interaction with that company, how many people in his tree may have at some point in their career actually worked at AspenTech? Do you have any idea? Can you provide any guess on that? I'll give you a moment to think about it while I'm introducing both of you. The speakers are Bill Mock and Ashok Rao. And Bill is actually an MIT person all through, bachelor's, master's, PhD, or science doctor, as you guys call it here. And he's the VP for R&D at AspenTech at Benford, I believe now. Ashok Rai has spent 30 years in his career working on basically every area that AspenTech would cover, 20 of those years at AspenTech. He is currently playing a leading role in the technologies of the asset performance management space at AspenTech. And he's based at Houston, Texas. So thank you.
Thank you. So we're going to be, my colleague Ashok Rao and I, we're going to be picking up on some of the themes that have been talked about over the last couple of days in terms of the use of data from the process plants and how to turn that into insights and action. So we'll be touching on some of the aspects that have been talked about already, but from the point of view of the software provider. Before I do that, I need to give a disclaimer. We're going to be talking about things which are visions for purposes of discussion and to stimulate discussion. I'm obligated to say that this does not constitute a commitment to deliver any of this as features or capabilities in the near future. Having said that, before we start, I did want to start off with recognition and thanks to George for his contributions to Aspen Technology. AspenTech has a pretty deep tradition in terms of academia, came from the Aspen project at MIT. However, over the past several years, I'd say that our involvement with academia has became a little bit ad hoc. So back in 2012, we decided to establish an advisory committee of leading academics to help us accelerate the innovations in the process engineering software that we develop, and also to promote the usage of process systems engineering software in universities. There was a comment earlier about in terms of developing the next generations. It's very important that certainly process systems engineering training is an important part of that education. So we decided to formally establish this academy, and obviously, who's the best person to help us to really bring that into play? It was George. George had very deep relationships with some of the members of AspenTech. And in 2012, George helped us to develop the Aspen Academy, developed a charter, as well as recruit a number of world-class people from academia to help us. So some of the founding members are here today. Jim Rawlings, Ignacio Grossman, and Larry Biegler, as well as others. This picture here is very typical of how George helped us. Maybe it's hard to read the text there, but basically this was an early workshop in which George was helping us to sort through ideas in terms of the potential for bringing these to commercialization in terms of some of the research that we'll be doing as part of the Academy. So over the last, over a period of 3 to 4 years, George really helped AspenTech in terms of forming that Academy to become really an innovation engine for AspenTech. We have developed, through our relationship with the Academy, we've done research in areas such as molecular characterization, optimization, process control, as well as analytics. So again, George, really want to thank you for your contribution and for helping us, especially these last few years. As we talk about, at this point in the symposium, I'm probably the 12th person to have given a slide about the evolution of process systems engineering, so I'm not going to spend a lot of time on it, but basically over the last 4 years, it's not only the scope of what is being modeled in process system engineering, but also the business processes, moving from design to operations to supply chain optimization and to maintenance. So as we have looked at this journey, we ask ourselves, where do we find ourselves today, and what are some of the trends that are impacting our industry? So I wanted to point out some of the technology trends which have been discussed somewhat. We talk about the Internet of Things, but really it's the industrial Internet of Things which is changing the process world as we see it today. There was a statistic that was given earlier by Tom Egger about how many Internet-connected devices there will be in 2020. I think he mentioned 20 billion. Gartner Group talked about 7 billion Internet-connected industrial devices, as opposed to just general Internet-connected devices by 2020. And many of those will be in the process industries, and we're seeing that today. So some of the market trends that we are seeing and some of the technology trends are that connected industrial devices are going to continue to proliferate worldwide. Sensors and equipment will become increasingly smarter with embeddable software in hardware, smart sensors, things like inferentials and calculations will be done as part of the sensing equipment. Industrial information systems will move more and more to the cloud for a number of reasons. One is just having the bandwidth and the computing horsepower. The second is because of the ease of deployment. Now, when we move these types of systems to the cloud, then we need to take into account aspects and considerations such as cybersecurity. And these connected devices will generate massive amounts of conditioned data about our processes and about the manufacturing plants. And as more and more of this data becomes available, manufacturers are going to look into how to mine that data for deep insights. So we want to talk in our presentation about the challenges and about some of the vision of being able to exploit that data for what we call asset optimization. But I thought it'd be useful to talk a little bit about the type of data that we're dealing with. So, this is an example of a month's worth of data from a plant historian for maybe a couple of dozen tags. And this is a wealth of data. Is there anything useful here or not? Yes, maybe, maybe not. That's one of the challenges that we need to look at. But this isn't the only type of data that our customers and manufacturing plants are dealing with. We also, the historian data has to have a context, and the context is often found in things like P&IDs, equipment data sheets, and things which really help to define the configuration, the connectivities, the control schemes that really make up the plant. And the equipment data sheets really have details in terms of the actual equipment constraints and equipment performance parameters that drive the plants. In addition to this type of data, another type of data which is becoming more and more commonplace is having 3D plant models. Most large capital projects have 3D plant models that are developed now. And this certainly gives you information about the plant layout, about the equipment layout, and obviously it does impose constraints on any optimization. Another aspect of data that we deal with is in terms of maintenance. Again, earlier somebody asked the question of what happens if something breaks down. Optimization is something which is going to be impacted by the reliability and availability of your process. This is an example of some maintenance records for a specific refinery unit. So if you have rotating equipment or centrifugal equipment, pumps and compressors and such that break down, that surely is going to impact the ability to optimize the process. And this is the type of data that traditionally maybe has not played as much into the optimization arena. And beyond that sort of structured data, there's unstructured data. There's operator logs and information that will have to be interpreted or could be interpreted and could provide additional insights in terms of the operation of the plant. So if we're looking at optimizing the plant or optimizing assets, what if you could leverage the rich wealth of asset data in design, operations, and maintenance to push the boundaries of what's possible and optimize the asset across the life cycle of the plant? What if you could leverage asset data to run the plant to the limits of performance and optimize the maintenance and reduce the downtime so that you can get more out of your plant? So those are the challenges. And looking at some of the technologies that are in play, such as smart sensors, big data, data science, mobile connectivity, cloud computing, modeling, AI, machine learning, some of the things that have been talked about over the last few days. What we'd like to do is to present maybe some ideas based on some of the things that we've been working on, as well as some of the things that our customers have been working on, in terms of how to leverage that data in terms of using it to optimize the asset. So at this point, I'd like to turn it over to my colleague, Ashok.
What I would like to do is now just present a different view on the same information that Bill just presented. If you look at this slide, for those of you who are familiar with real-time optimization, the steps below are reasonably clear: capturing data, organizing it, predicting and prescribing, ultimately implementing the actions. What's different about this diagram is that now we're not only dealing with continuous information or operational data, time series data. We're dealing with maintenance data, whether it be design data, or it could be other sources as well. And the other sources are not necessarily structured data, they could be textual data as well. So what we see as our vision is that given this wealth of data sources that span a whole host of possible areas and structures, whether it be structured or unstructured, there are challenges that come in that first you need to pull the data together. And that is the consolidation, aggregation, the cleaning of the data becomes crucial. Now that the data is in different contexts, how do you pull it together? How do you make sense of the linkage? Once you have data linked and appropriately structured, the next challenge is how do you derive insights from it? And what we see is that we can, by bringing together all the design, operation, and maintenance domains, we can subject it to a whole stack of what we would call an ensemble model. And our definition of an ensemble model here is a combination of first principle models, empirical models, perhaps machine learning models, statistical models. So all of them play a role. What we've seen is that each of them has its specific niche, and together they prove to be very, very powerful. So given that if we can combine that together with the appropriate workflows and the appropriate rules, then what do we get? What we can provide then is operational, maintenance, as well as design guidance. Now, it is an optimization problem. The objective is the minimization of overall plant lifecycle costs. What are the constraints? You look at the design risk, the operational risk, and the maintenance risk. We have to be able to quantify that and be able to say that this is the amount that an organization is capable of tolerating. And given that, if we could guide with an objective to minimizing the plant lifecycle cost, that would be definitely our vision for asset optimization. Now again, this is after all a vision that is based on certain work that has already been done and a lot of work still to come. And here's a view. What we see are the technologies that will enable this vision. Now in the data collection area, there is a lot of work that has already been done. I mean, there is a whole host of abilities right now to collect the data, whether it be from in a wired sensor or a wireless sensor at fast speeds, and you can actually get all the operator records. And again, the question, of course, becomes, the challenge is how do you pull them all together? And for that, again, we have a number of technologies that are, again, all the big data technologies, whether it be Hadoop or Spark capabilities. Now, trying to pull all this together, what we've seen is that operations that would typically take hours to do, because we can enrich the information a priori, run it when the computers are still, in a way, quiescent, not being used in an intense fashion. And if you can collect all that information, enrich the data, you might actually achieve big data in the process industries. Our sense right now is we're not at the big data stage, given only the information, say, in the historians. But when we pull together all this information and enrich it appropriately with our modeling capabilities, we will reach big data. And we will require all the capabilities that are being developed by a whole host of systems outside the process industries. Now again, once you have the data, what do we do about the insights? We've tried to put together a few here. We've talked a lot about process modeling. A little bit more, we'll talk about molecular modeling as well. And ensemble modeling is what I mentioned as more a stack of models, not necessarily any one particular modeling technique in a particular case. The key thing is that this can be now powered by a whole host of other newer technologies that are coming in: machine learning, knowledge graphs, cognitive computing, natural language processing, and together they should enable us to provide prescriptive guidance. And really the goal is that at the end, that both in terms of messaging and actions, we should be able to actually implement these solutions. And here are a few examples. If you take, of course, no need to explain closed loop control, or to define where do we need to have a sensor. If we could actually go in and prescribe and tell you that, that's a step forward from where we are today. And determining what the spare part inventory ought to be like, or what work orders should be scheduled, what design improvements should be made. These are all ultimate targets. I mean, typically, we've talked about closed loop as being closed loop control. Here, we're expanding the vision to include a lot more than just the continuous control aspects. What I would like to do in the next few slides is actually touch upon a few areas where AspenTech has made some strides, and it might help set the background into the work that needs to be done still. So I'll begin with the area of data science, where, as Bill just pointed out, there is a lot of data in the historians. And the data tends to be such that visual observation and trying to determine that this pattern recurred at a previous date in a certain way is difficult. So there have been a number of moves towards, and again, a lot of these techniques were used in the medical field quite a bit, and now we're trying to incorporate them into the process industries. Pattern discovery is a capability where all the user needs to provide is the length of a particular pattern and a tag name. And with those two pieces of information, the system, the algorithm, is able to traverse the historical data set and pull together patterns that recur and even categorize them into different groups so that you have different patterns that recur at different points in time. How does this help? You will see in the following slide, I mean, this is the kind of the foundational building block of root cause analysis that we can perform. So we'll get there in a moment. If you did not think about pattern discovery, discovery is without much of a user input. If you really had a priori knowledge, you were looking at a particular pattern in the time series and wanted to see whether it recurred in the past. And this could be a single variable or a multivariate pattern. That is possible today. What you're seeing here is actually screenshots from software that AspenTech has already released. There is work that's also been going on how to visualize the data. Now, we spoke about visualization having limitations, but if visualization is done in a fashion where you compact it down, for example, you're looking at a time dimension. If there was a way to look at data on a monthly basis and be able to compare the 12 months of the year and immediately visually identify that the winter months, the behavior of the plants very different from the summer months or any other such deduction you could make. And this would be exceedingly powerful. And that's it's basically a bitmap that is probably a 4x4 or an 8x8 bitmap where the colors are not necessarily representative of actual values. They are in aggregate, they represent the way a person would distinguish between different time series. So again, more work going on in that field, but this is a powerful area. The area of root cause analysis, again, a nascent field, very powerful. What I mentioned earlier was pattern discovery, the way to find patterns automatically. The algorithm can do that. And let's assume that here, what you see in the various vertical lines here are different events that have happened in time. This could be an entire year of time series history. And this event could be an emissions event, for example, that occurred at a point in time. And the intent is to carry out a root cause analysis. The typical way that is done today is a Six Sigma project. So where a root cause analysis is performed, perhaps a lot of work goes into it in terms of diagnosing what happened, what may have happened, fishbone diagrams are drawn up, etc. What we do here instead is that the entire feature extraction is done by data science. So what you're looking at here, that bar represents in a way the event window, the time surrounding the event. And what we can find is that there are certain precursors just prior to that event. And it uses Bayesian approaches to generate this causal map. This causal map has the y-axis is actually time. What you're looking at the bottom is actually the event. This is the event node. And you're seeing the links between all the precursor nodes and the event node. And this time domain, again, I won't go into the details, but you can actually see small snippets of the time series and each node. And once you train this model using past historical events, you can then subject it, you can put it online, and when subjected to real-time data, it'll give you a sense of the high probability of a particular KPI spike. Now, this entire workflow is something that, if conducted with typical Six Sigma approaches, might take weeks, may take months to conduct. This could be, I wouldn't say hours, but it could be hours, could be days, but it is a significant step beyond where we are today. Again, what I would like to just add here is not all techniques that we're talking about here, some like PLS and PCA modeling have been with us for a long while. The key is how do you blend such capabilities with the other capabilities that you're just seeing. The latent variable modeling technology with regard to multivariate analysis, very powerful, enables you to do data conditioning, anomaly detection, determining the key contributions to a particular event. And now, when you think about this, you realize that combining this with what I just spoke about in the root cause analysis domain could become even more powerful. Root cause analysis deals with the ratio of abnormal to normal events being very small. So you have spikes occurring infrequently, while PCA-PLS analysis, the ratio of abnormal to normal would be relatively larger. So there is a gray area. There is a need to understand where one technique stops and the other one takes over. And so that's the challenge we're trying to address today. Molecular characterization is something, again, when you think about the data from what you can get from crude oil, say, for example, if you look at the crude data, it could be only 20 points of data for a crude, could increase to 100 points using distilled cuts. If you go on to GCs, you will get 1,000 points, and this is actually 50,000. That's Fourier transforms using mass spectrometers. So you could get 50,000 points of data. Now, if you took those 50,000 points of data, we create a molecular characterization model, and that model helps us characterize the molecular distributions within the crude. Ability to do this implies that now we can create a much more fundamental understanding of the process itself. So you're looking at two regions here. One, we're coming at it from a data science perspective, the other from a molecular modeling perspective. And where do they intersect? They intersect in areas like these. This is an area which George may remember. He was the one when we initially presented these ideas to him. He kind of critiqued them, and I think you gave us a lot of insights into how to proceed here. This is combining data science, first principle and empirical modeling for equipment analytics. And what we have done here is specifically for distillation. But the distillation example is just an example. This could be the way of the future in terms of how data science, machine learning, first principle modeling, empirical modeling, all of them come together. And it does in this particular case. This product starts with an Aspen Plus model, enables you to, of course, connect it to real-time data. Again, all this has been done many times in the past. It is a key question that was previously asked earlier. How do we do this for the mass market? This is the kind of the attempt for the mass market audience. So where the entire tuning of the model with using historical plant data is done automatically, the entire calibration process, the parameter estimation, all that is done pretty much in the background. And ends with a view that an operator can use, which includes a detailed look at the stability diagram of the column, the internals in terms of the liquid and vapor flow rates. And on the other hand, alerts as to when you could encounter flooding in this column. So a lot of, and again, the basis for all this is an ensemble model. It uses first principle models, it tries to kind of create a pseudo-dynamic model using empirical techniques, and then there's pattern recognition involved as well to add it from the raw data, and that all combined together basically gives you this view. And just like to touch upon on the maintenance front, again, we are having equivalent efforts. Here we're combining sensor data on one hand and asset work history on the other, two different data sources, creating smart trained agents that can assist in asset monitoring as well as failure prediction. And the failure prediction in this case, the interesting things are that normally when you talk about operational issues, you can give early warning of hours, maybe minutes and hours. In the mechanical maintenance space, you can give early warning that goes to weeks and months. And that's where we are at right now. Just want to touch upon, I'll give you a little bit of a picture. Just want to say, I picked a few of the areas where I believe there's a lot of work to be done. Cognitive computing Many people think of this as the next level beyond descriptive, predictive, prescriptive analytics. So where natural language processing is used as a communication device to greatly improve our ability to interact with the analytic. Others see it as, well, it does not need to be another level of computing. It can be an addition to what we already do. Knowledge graphs are a capability to, since we have data from different domains, whether it be the maintenance, the operational, the design domains, pulling them together without replicating all the information, you need some way to draw those connections, and knowledge graphs may help there. I've already spoken about ensemble modeling. We've begun on that long journey of stacking the models and getting to use them where appropriate. I believe there's a lot of work to be done in terms of the rules and the workflows that are appropriate in each case. The prescriptive engine, again, a lot of work there as well. We have begun that work in terms of providing prescriptions in many of our analytics. However, the prescriptions are still contained, finite. They are not automatically probably deduced from the scenarios that are being exercised. And so there is a lot more work in that regard. And many of the answers are in the different views that I already showed you, that we just need to work on those, and I believe others are working as well. So where do we see this? We see that these capabilities empower the next generation of process engineers. What does it bring to the table that is new? We have definitely engineering, modeling, and optimization has been the bedrock of a lot of the work done so far. Now we add in the data science, the machine learning, and the analytics, and together, and not separately, together, I think they make for a much more powerful set of tools. In closing, we would like to, on behalf of Aspen Tech, I would like to thank George for all the insights that you have provided us, and I think you see the results of many of your insights here. And I'd like to applaud your contributions to the academic community and wish you the best in your retirement. Thank you.
Thank you. Any questions?
Yeah, thank you. Such a superb slide that we have seen here. So I'm Zeta from MIT. Basically, this attracted me much on how we increase the employability rate of the graduates, especially for the final year student, because most of the process engineers, they know about the Black Belt, Six Sigma, and so on when they enter the career world, because the consultation comes during that time. So one of the alternatives that we can do is actually to embed this kind of subject into the final year subject for the undergraduate students. For example, they learn about DOE, the process optimization to optimize any process yield or production rate and so on for the design of experiment class. So what if we can do, instead of coaching the engineers industry, so we coach the students in the class itself. Of course, there's no real data. Of course, we don't have that, but the lecturers may need to find some collaboration with industries to get some data and to do it together with them in the class, so that before they enter the career world outside, they actually have this kind of optimization skill when they were in the graduate's time. So that is one of the important insights that I get from your presentations.
Thank you. We were actually, before the talk this morning, we were having a discussion with Richard about some of the curriculum at MIT, and I guess there's a graduate student course where actually they do bring in some of the data science, machine learning. As we said this earlier, the question was asked earlier, where are the people coming from that are going to be able to work on this? I think part of the evolution of the curriculum is to be able to support some of these concepts. We hire people who are chemical engineers, and we teach them data science, and that's something obviously chemical engineers can learn anything, right? So that's something that I think will become naturally, I think, part of the curriculum as the industry evolves.
Joe?
Thank you for a very nice talk, Bill and Ashok. I would make a comment first. This has a lot of echoes to me, but anyway. Yeah, I'm very glad to see the simulation company, the world leader, AspenTech, is looking into data and data analytics. I think that covers a whole spectrum of things that the industry needs. Another comment is about this, one of the techniques you mentioned about doing trend analysis, finding patterns and the signatures in the data. This is, I think, a tribute to George, who actually worked on that 20 years ago. There are a couple of papers we all remember between George and Babak Bakshi. So I think then it kind of disappeared in this PSC area for 20-some years. But I know that's a big activity going on in this time series data mining area for the last maybe 15 years or so. So somewhere else, the thing has been in sort of high development mode. So I guess my question or / comment is there are activities elsewhere, and there are a lot of them elsewhere, especially in the data mining and time series data mining. And for our problems in the process industries, a lot of the data we have are actually time series data. They are highly dynamic because we have feedback control. We even have high level feedback, even this optimization in real time. So those are all the levels of feedback that brings in a lot of the dynamics, different time scale, and so on. So I guess my question is perhaps, it's really not a question, perhaps there'll be a lot more effort looking into how we should focus on the dynamics and the high dimensional time series data for this industry and area. Yeah.
Thank you, Joe. I think Joe has been also instrumental in helping us in understanding this area as well. And the dynamics of the process are definitely crucial. The fact that there are so many timescales involved, and I think we've had so many discussions on the fact about where the applicability of different techniques, given the very fast-moving systems, or when how the key questions that always arise is, I think the practice so far has been, we can do all the things necessary, but we can do them with a person involved, the expert involved. How can we automate or make this more, I wouldn't call it dumb it down, I would say make it easier for non-experts to actually utilize these techniques. And that's been the constant challenge. I think Professor Venkat in the audience, Joe, there have been many people here who have been helping us in trying to identify areas of work that can be automated such that we can do a better job of handling the dynamic systems.
Let's thank all our speakers.